How do you debug quantum Fourier transform implementations? Imagine trying to tune a complex musical instrument where each string must vibrate perfectly. That's what debugging a quantum Fourier transform feels like. It's a key part of quantum computing that turns quantum states into their frequency components. When you implement it on real hardware or in software, mistakes can sneak in. So, how do you find and fix those errors? First, start small. Build a simple quantum Fourier transform circuit with just 1 or 2 qubits. For 1 qubit, it's just a Hadamard gate, which creates a superposition. For 2 qubits, add controlled phase rotations. Check if these basic circuits produce the expected results. If they don't, you know there's an issue with your gates or their angles. Next, use quantum simulators. These tools let you see the entire quantum state before and after applying the Fourier transform. Compare the output with the mathematical solution. If they match, your implementation is likely correct for that case. If not, trace back through your circuit to find where the state diverges from the expected. This helps you pinpoint the problem. Make your code adaptable. Write your quantum Fourier transform so it works for any number of qubits. Test it on small sizes first. Once it works reliably, increase the number of qubits step by step. This approach helps catch bugs early and makes your code more reliable. Compare your implementation with trusted libraries. Many quantum programming frameworks like Qiskit, Q#, and PennyLane include built-in quantum Fourier transform functions. Run your version and the library's version on the same input. If results differ, look closely at your code. This comparison can reveal mistakes in your rotation angles or gate sequences. Insert checkpoints in your circuit. Use diagnostic operations like state dumping or mid-circuit measurements. These let you see what the quantum state looks like at different points. For example, if a phase rotation isn't working right, you'll notice the state isn't evolving as it should. This helps you find the exact step where things go wrong. Try running the inverse quantum Fourier transform. If you start with a known output state, applying the inverse should bring you back to the original input. If it doesn't, the problem might be in your forward transform or in specific gates. This method helps isolate issues. Automate your tests. Write scripts that generate different input states, run your quantum Fourier transform, and compare the results automatically. This is especially useful as the number of qubits grows. Manual checking becomes too slow and error-prone. Automation saves time and catches bugs more effectively. Remember, hardware noise can also cause discrepancies. When testing on real quantum devices, noise and errors can mimic bugs. Always verify your implementation on simulators first. Once it works perfectly there, then test on hardware to see how noise affects your results. Debugging quantum Fourier transform implementations is a step-by-step process. Start with small circuits, use simulators, compare with trusted functions, check intermediate states, and automate testing. This approach helps ensure your quantum algorithms work reliably, paving the way for more complex applications like factoring large numbers or estimating phases.